Hello there! In this session we are going to talk about the primitives of rational functions. This video is the second part of the previous lesson. The objectives we aim to learn in this session are to know how to calculate more complicated primitives of rational functions and to understand the technique and process. What do we need to grasp for today's lesson? Essentially, we should comprehend simplifying fractions, the primitive of power functions, the primitive of logarithmic functions, and the primitive of tangent functions. In this instance, our primary focus will be on the concept of the tangent primitive. A rational function is essentially a function defined as the ratio of polynomials, with a polynomial p in the numerator and a polynomial q in the denominator. An important and practical process. For the computation of rational integrals is the method of partial fraction decomposition. This method states that a function defined as a ratio of polynomials, known as a rational function, can always be expressed as a sum of a finite number, typically denoted as f1, f2, fn. This means that each of these smaller functions have different types. The first one is a polynomial. It can only exist one, therefore there is only a single polynomial. And then the others fall into one of these categories, either a factor of the form x minus a, or a factor of the form x minus a raised to an exponent, or a factor of the form x plus b derived from a quadratic polynomial raised to a power, with a quadratic polynomial being irreducible in the real numbers. The first three types have an elementary antiderivative, polynomials. The second type includes logarithmic functions, and the third type comprises power functions. In this session, we are going to focus on those of type 4, and in fact, some of the type 4 can turn out to be much simpler. Those are the ones that have the exponent n in the denominator worth 1. As we will see, the methodology to solve this type of primitive is quite standard and is always the same. Before we take a look at an example, we must remember that thanks to the linearity of the integral, if we want to calculate the primitive of f, if we have it decomposed as f1, f2 and fn, the integral of f would be the integral of the first one plus the integral of the second one plus the integral of the last one, basically the sum of all of them. This is positive since we convert the primitive of a complicated function into a sum of simple integrals. Let's see the integrals of type 4 with a practical example. Let's remember once again that type 4 integrals have a polynomial above, ax plus b, and below a polynomial of degree 2. In this case, we will take it raised to 1, where ax squared plus bx plus c happens to have no real roots. Well, we now take the primitive. And let's see the process that we are going to do very mechanically. The first step we do is take the denominator. What are we going to do to that denominator? Well, we are going to derive it. Once it's derived, we notice that its derivative is 2x plus 2, and now we try to find that same 2x plus 2 in the numerator. We go to the polynomial above, we see that the coefficient of the x is 3, and that it doesn't really match with the 2 that we just got. We have to turn it into a 2 somehow. How do we do that? Well, what we'll do is we'll put the function exactly as it is. The denominator, I leave it untouched. And now what I do is multiply and divide by a number to get the coefficient of x to be exactly 2. In this case, I would multiply by 2 divided by 3, and I would also divide by 3 divided by 2. The result we're left with is exactly this. We're left with the 3 divided by 2 out, and then above we've got 2x plus 2 divided by 3, which is exactly what we wanted. Well, this step could be omitted if we didn't have a in the numerator. In other words, if we had a number above. If the top part happened to be just a number, the integral that we will see now would not come out. However, let's continue with the process that is, in a way, the most complicated part. Once we reach this point, we realize that in the numerator I still don't have the derivative I needed, which is 2x plus 2. We check it, and indeed I need to have 2x plus 2 above. So, what can we do then? Well, I copy everything exactly the same. The exact same integral, let's not forget the 3 divided by 2 that has appeared just a moment ago. And now we leave a little gap between the 2x and the 2 divided by 3, that is between the linear term and the number. And what happens now? Well, we are going to add and subtract the missing number. Since in this case we are missing a 2, we add and subtract that same 2. That way, if you look at it closely, what we get is that the first two addends of the numerator are going to be exactly the derivative. Now I would separate that fraction into two. On the one hand, 2x plus 2, and on the other hand, the minus 2 plus 2 divided by 3. After completing this step, we observe that the first of the integrals, that particular function, corresponds to a polynomial of degree 2 below, and simply its derivative above. We must remember that this aligns perfectly with the logarithmic type of primitives. Therefore, this primitive is simply the natural logarithm of the denominator, which is the natural logarithm of x squared plus 2x plus 2. Let's not forget that the primitive has an absolute value, but in this case, the polynomial is always positive. That is why we can remove the absolute value. Well, you might be asking, what should we do with the second addend, right? By simplifying a little bit, the second summand, we do the math with the coefficient, we take it out, and it would be minus 4 divided by 3. And now, I am left with the integral of 1 divided by x squared plus 2x plus 2. And that integral belongs to the arctangent type of integrals. One number above and below, we have a non-reducible degree 2 polynomial. Here again, it is crucial for the polynomial in the denominator to be non-reducible. As we well know, once we have this integral, the process we must proceed is quite simple. First, we put back the logarithm, and in order to calculate that integral, what we do is to take the denominator and apply to the denominator the completion of squares. Let's observe that the coefficient multiplying the integral has changed. This change occurred because I added 3 divided by 2 to each of the terms. Specifically, 3 divided by 2 of the first term, and 3 divided by 2 of 4 divided by 3 for the second term. As a result, we are left with 2 times the integral. After completing the square in the denominator, we recognize that the integral takes on the arctangent form. At this point, we observe that it's a squared function plus 1 in the numerator, and in the denominator the derivative, which is simply 1. Consequently, the primitive function is the arctangent of the polynomial enclosed in parentheses. Therefore, it's the arctangent of x plus 1 plus a constant. As we can see, resolving this type of integral involves a long process that consists of several steps, but it is always mechanical, so once one learns the different steps to follow, it is quite simple. And this has been all so far. After today's lesson, we should be able to calculate the primitives of most of the rational functions. In this case, of those of type 4, and also the ones formed by those of type 1, type 2, and type 3. Thank you all for your attention. See you in the next video.